Hello and welcome to Mr. Clee's video, second video in the series for Chemistry Unit 4 for periodic table on ionic bonding. The aim of this video is twofold, that by the end of it I will have shown how to use dot and cross diagrams to describe how an ionic bond takes place and to represent them, and to link this to the physical properties of ionic compounds, i.e. how they behave under what circumstances. So the key features of an ionic bond are that they always take place between a metal and a non-metal. They involve the exchange or the movement of electrons to result in in atoms, or now ions, with full outer shells of electrons. Because of the exchange of electrons, our ions end up with charge, and they're always drawn with square brackets. So from the previous video, you should know now how to construct the basic structure of an atom using its entry in the periodic table. This is the key number that you need to be aware of when looking at electron structure. Sodium, it has the atomic number 11, so it has 11 protons and 11 electrons. In an atom of sodium, these electrons are arranged in shells, 2 in the first shell, 8 in the second shell, and 1 lone electron in the third shell. The concept of the ion centres around this phrase, the full outer shell of electrons. As you can see in the atom, sodium has 1 electron in its outer shell. There are 2 ways for it to get a full outer shell. One is to gain 7 electrons, filling up that third shell, but a much easier way is to lose this single electron in its outer shell. By losing an electron, remembering that electrons are negatively charged, we end up with a positive sodium ion. It only has 10 electrons. Because it's lost a negative, it becomes positive, and it's drawn with square brackets to show that it is different from the original atom. You can do the same on the right hand side of the periodic table in group 6s and 7s. Chlorine here, 17, the atomic number, therefore it has 17 electrons. This time displayed as crosses. Because it has 7 electrons in its outer shell, 2 ways to get a full outer shell of electrons, one very difficult way of losing 7 electrons, and one much more straightforward way of gaining an extra electron. When this extra electron is gained, chlorine has gained a negative charge, which results in it becoming overall electrically charged negative, which is shown up here with square brackets. The now full outer shells of electrons do lead to particles that have charge. They're either positively charged if they're from group 1, 2 or 3, or negatively charged if they're from group 5, 6 or 7. If you take, for example, magnesium, which is in group 2, when it becomes charged it loses 2 electrons, so it becomes +2. If you take oxygen, which is in group 6, when it becomes charged it loses 2 electrons, so it becomes -2. Whenever you're doing charge, the charge goes superscript at the top, rather than when you're doing the chemical formula for something like O2, which is 2 oxygen atoms combined, where the number is subscript. It's a little trick that you can do to predict the charge on any ion from any group of the periodic table. If you remember that all the atoms in group 7 have 7 electrons in their outer shell, therefore they have 1 space, therefore when they become charged, the charge that they gain is -1. In group 1, 1 electron in the outer shell, so they lose 1 electron, becoming +1. That is mirrored throughout the periodic table. So everything in group 1 forms ions that are +1. Everything in group 2 forms +2 ions. Everything in group 3, like aluminium, forms +3 ions. Everything in group 5 forms -3. Group 6, -2. Group 7, -1. What you tend to find is that things involved in group 4 are more often associated with covalent compounds, and group 0 or group 8 at the end here, they already have a full outer shell of electrons, and for that reason they don't form ions. They very rarely form compounds at all. This might be a good opportunity at this stage to practice drawing a couple of ions. For example, beryllium. It's nice and easy and nice and quick to draw. Maybe fluorine, just to show the electrons being lost and gained, and the associated charges. So as you've probably noticed, these positives and negatives can pair up. Sodium chloride, which was the example given before, the sodium atom will lose its electron to chlorine, forming a sodium ion and a chlorine ion. These are then bonded together in the form of sodium chloride. This is the case with any ionic compound. The electrons are lost by the metal and gained by the non-metal. In this example here, what you can see is the formation of sodium oxide. Sodium has a charge of +1, and oxygen has a charge of -2. The way I like to think about this is when you're predicting the formula of an ionic compound, you have to put all the positives on the right hand side and all the negatives on the left hand side of a seesaw. This seesaw must be balanced. Currently, the seesaw would not be balanced because you have more negatives than you do positives. In order to make the seesaw balanced, you have to add in an extra positive. It's a bit tight. Meaning that overall you have 2 sodiums and 1 oxygen, which is written out in the form Na2O. This procedure can be used with any positive and any negative ion to predict any ionic compound. It could be magnesium fluoride, which would be MgF2. It could be aluminium oxide, which would be Al2O3. They all work in this way, as long as you remember that the number of positive charges has to equal the number of negative charges. So when these ionic bonds form, what you end up with is lots and lots and lots of positive and negative charges attracted strongly to each other. This locks the ions in place in a structure that's described as a giant ionic lattice. Lattice is a bit like the top of a pork pie, where the pastry is interwoven through each other. The giant bit tells you it's repeated over and over again. But the main principle is that you've got positives and negatives surrounded, really strongly attracted to each other. Very, very, very strong bond. Because of this very, very, very strong bond, you end up with very hard materials. It's hard to break the bonds between the ions that have very high melting points. You can see here the melting point of sodium chloride is about 800 degrees, and magnesium oxide, which is close to 3000. However, these materials are soluble in water, and because the ions involved do have charge, when the ions are free to move, i.e. when they're soluble or when they've been melted, when they're molten, the ions can move in response to an electric current. So ionic compounds do conduct electricity when they're dissolved or when they're liquid. They don't, however, when solid, because those ions are then not free to move. Thank you for watching. That concludes my video on ionic bonding. Just remember, as I said before, in an ionic bond, it's always between a metal and a non-metal. We get the exchange of electron resulting in full outer shells. This leads to particles that have charge, called ions, and we always include square brackets. This then links to the physical properties, because we end up with very hard materials, very high melting points, that don't conduct electricity when solid, but can when molten or dissolved in a liquid.